Greetings, and thank you for attending this presentation. My name is Zhou Zhao, and I'll be presenting today for our optimal control-based eco-RAM merging system for connected and automated vehicles. Before we get to the main content, I would like to start with the outline of the whole presentation. In the first section, I'll give the introduction of the work. Then I will formulate the problem in the mathematical way, and I will go through the system architecture and discuss the detailed modules in section 3. Next, I will expatiate the methodology used to solve the proposed system. The simulation study will be introduced in section 5, and in the last section, I'll talk about the research plan of my future work. RAM metering is a widely used RAM merging management method, which utilizes traffic signals to regulate the inflow rate of traffic entering the mainline in response to real-time traffic conditions. RAM metering usually consists of a two-phase signal light, together with a signal controller. It has proven to be a cost-effective operational strategy to improve mobility metrics and environmental impacts. However, since RAM metering introduces stop-and-go driving, for RAM vehicles, it increases travel time and energy consumption. Also, RAM metering compresses the distances that merging vehicle has to adjust their speed to merge into the mainline stream, potentially increasing the safety risk and fuel consumption. The contributions of our proposed system are related to the following issues of existing work in this research field. Energy consumption. Utilizing CAV techniques, many researchers have been trying to design a cooperative control system between vehicles in the RAM merging area to improve mobility metrics. However, few of above approaches take energy consumption as a major focus in the problem formulation. Entrance sequencing. Although previous research proposed many sophisticated control methods, they failed to fully consider the entrance sequence of both mainline and RAM vehicles into the merging zone. The first come, first served strategy and simplified estimated time of arrival scheme are commonly used. Inflow regulation. The cooperation of vehicles in the merging area proposed by existing research can only improve the local performance of the system. The unregulated inflow rate of the RAM vehicles can still lead to potential oversaturation of the highway network, thus increasing the risk of upstream congestion and traffic accident around the merging area. Macroscopic traffic simulation. Existing research have not fully utilized comprehensive traffic simulation tools. Obtaining results from a snapshot of vehicles with numerical simulation cannot well represent the long-term impacts on the traffic across a wide variety of scenarios. Our previous paper proposed a concept of a hierarchical system for corridor-wide RAM control. At the corridor level of the system, a cooperative protocol can be introduced to calculate the system-wide optimal inflow rate for each on-ramp, giving the estimate of macroscopic traffic conditions. The RAM level controller coordinates the maneuver of CAVs locally at each RAM area and regulates the inflow rate accordingly. In this paper, we focus on the development of the RAM merging control subsystem by assuming the suggested RAM inflow rate to be given as input. The proposed study assumes a second-order dynamic for vehicles. Since we only control the longitudinal dynamic, we set up a one-dimensional coordinate system. and map the positions of vehicles on both mainland and RAM to this system. Using state and observation of a group of vehicles defined in this slide, the system can be formulated in a linear form. Then we formulate the cooperative merging as an optimization problem in a quadratic form by balancing the tracking error and the control effort. To handle the continuous flow of the incoming traffic, we first specify the roadway segment with two types of zones, control zone and buffer zone for the on-ramp and mainland as shown in the bottom figure. In the control zones of both mainland and on-ramp, a centralized processor is employed to receive and process the incoming information from CAVs and send the control signals back to the CAV to achieve system-wide energy efficiency. Buffer zones, shown in orange, are located on the upstream portion of the control zones and are designed to continuously monitor the incoming vehicles and collect information to support subsequent control decisions. The hierarchical architecture of the proposed RAM management system is shown in this slide. In the data collection module, vehicles' information is collected once they enter the buffer zones triggered by an event-based scheme. Because the controller is designed to regulate the vehicles to form a compact string, it is important to know the entrance sequence of the vehicles into the merging zone. Intuitively, the sequence would have impact on the string-wise energy consumption. Therefore, instead of using a heuristic sequencing protocol, such as first come, first serve, we develop an optimal sequence determination module to identify the most energy efficient sequence. The module can examine all possible sequences, apply the finite horizon linear quadratic tracker to predict the controlled speed profile of each individual vehicle, estimate the associated energy consumption, and select the least energy consumption sequence for the vehicle level control. For the vehicle level, two types of control are involved. The RAM leading vehicle would be controlled to regulate the RAM inflow rate, and for all CAVs in the same group would be controlled together cooperatively. RAM leader is the first on-ramp vehicle that does not pass through the buffer zone and has not been controlled. A RAM leader can trigger the vehicle grouping process by hitting the trigger point. All the vehicles in the buffer zone will be then controlled as a group. The length of the on-ramp buffer zone is predefined, and the length of the mainland buffer zone is adapted to the real-time traffic condition, such that the number of vehicles in both RAM and the mainland can always match. For each group, we will first exhaustively generate all feasible sequences, and the trajectory of each vehicle can be calculated by solving the optimization problem present in the previous slide. Using finite horizon scheme, the solution can be calculated iteratively using the Riccati equation shown here. Q and R parameters are fine-tuned to keep the balance of tracking error and control input. Then we estimate the energy consumption for each possible sequence of the vehicle with the predict trajectories. Finally, the sequence with the minimum energy consumption will be selected as the optimal sequence. Next, two types of speed control are introduced here. When the estimated time of arrival is earlier than the proper arrival time derived from the RAM inflow rate as required from the corridor level, we applied a linear controller to slow down the RAM leader till it hitting the trigger point. For coordinating the group of CAVs, we use receding horizon LQ tracker to control each group of the vehicles given the optimal sequence. Here the Q and R parameters are as same as the finite horizon LQ tracker used previously for optimal sequence prediction. To better illustrate the whole process, the example trajectories are shown in these figures. Left side shows the RAM trajectories, and the right side shows the mainline trajectories. Let's focus on group 2. Before the RAM leader hitting the trigger point, it is controlled for regulating the inflow rate, which shows in blue curve. All the uncontrolled vehicles show in yellow curves. Once the RAM leader arrives at the trigger point, the length of the mainline buffer zone is determined accordingly, and all the vehicles in the buffer zone are collected and controlled cooperatively, which shows in orange curves. We coded a real-world RAM merging environment in PTV VISSIM as shown in the left figure. Different from the numerical simulation that most of the previous research utilized, traffic simulation can offer more realistic real-time interaction between the equipped vehicles and other traffic in the network. This enables a better observation of the impact of the proposed system on the whole traffic over time. Through the driver model API, the behavior of the CVs in the network can be controlled with the proposed algorithms. Uncontrolled vehicles in the network are modeled by the default behavior in VISSIM. In our simulation, the conventional RAM metering system and the RAM without any control approach are introduced for comparison. As shown in this video, in no control scenario, RAM vehicles severely affect the mainline traffic and cause shock waves. For RAM metering scenario, although less effect to the mainline traffic, long queue at RAM is generated because of the stop and go maneuvers. For the proposed system, the system flow is smooth and stable. The tables in this slide show the performance of the proposed RAM management system in the perspective of mobility and fuel consumption. The mobility performance is measured by network efficiency using total vehicle mile traveled divided by total vehicle hour traveled. The result confirms that under the regulated inflow rate, the proposed system can avoid potential traffic congestion and improve mobility up to 147%, with a 47% fuel saving compared to the conventional RAM metering and the RAM without any control approach. An ongoing research direction is to develop the upper-level corridor-wise perimeter control algorithm, which can provide the optimal RAM inflow rate cooperatively for each involved individual RAM along the corridor. In addition, more practical considerations on the mixed traffic scenario would be one of our future steps. This research is supported by National Center for Sustainable Transportation. That's it for the presentation. If you have any questions or comments, please feel free to contact us.